Hi everybody. So the next section 5.3 is on complex rational expressions, and so what we'll look at in this section is simplifying a complex rational expression by simplifying the numerator and denominator separately, and then we'll simplify a complex rational expression by using the least common denominator. So a complex rational expression is just something where you've got a fraction within a fraction, and so there are sort of two ways of doing this. This first method we'll call method 1. Basically what you do is you might have done this with numbers when you were younger, but basically with method number 1, you just add the fractions together on the top, add the fractions together on the bottom, and then flip the bottom over and multiply. And then there'll be another method which is sometimes called method 2. I don't really care which method you you call which, I guess, but the second method, you basically try to find the least common denominator of all the fractions sort of within the big fraction, and then you multiply the numerator and denominator by that common denominator. And so if you think back to problems that you might have done when you were younger, where you had to add and subtract things, where you had fractions within fractions, we're basically going to use the same method we did there, except now again the fractions won't just contain numbers. They will contain x's and things like that. So in this case, let me maybe more clearly define what I mean by a complex rational expression here also. Basically, a complex fraction, then, like I said, is something where you have a fraction within a fraction, right? Something like this, where you've got a numerator and denominator, but then within each numerator and the denominator you might have fractions as well. We won't simplify this one, but this would be an example, right? And so to simplify complex fractions, there are two methods, the two methods I referred to earlier. You can use whichever method you prefer. I probably won't expect you to do it both ways on the exam. Now, in some cases, method 1 might work better than method 2. I think in some cases, method 2 can be faster, but it's maybe not as straightforward. So whichever you want to do, I guess I tend to like method 1, but you can certainly use method 2 if you want. So for method 1, as I indicated earlier, you basically write both the numerator and denominator as a single fraction. So just going back to that example we were just looking at here, you basically write this as a single fraction by adding, and then write this as a single fraction by subtracting. So you basically simplify the numerator and denominator, and then you basically flip the bottom fraction over and multiply, right? Because you're basically dividing a fraction by a fraction. So you'd want to flip it over and then multiply. And then just make sure that you reduce, right, your answer in lowest form. So here's an example of the first method. So we don't really have to do anything to the top here because the top is already a single fraction. But for this particular problem here, I would need to get a common denominator. So in this case, the common denominator for the two fractions on the top and bottom would be c squared. So I'd have to multiply on the top and the bottom by c here. Right, that would give you 7c over c squared. Again, since I've got the common denominator now, I would just add the numerators together and then just bring the common denominator along for the ride. So remember, you do not add the denominators. Now I've got a fraction divided by a fraction, so I would just simply flip this fraction over and then multiply. Again, you might be able to reduce before you multiply. So for example, right, this c here will cancel with one of those c's, leaving you with 4c over 7c plus 2. Or you can multiply first and then cancel, whichever way you want to do it, right? But in the end, you should wind up with the same answer. Now, I should mention that it shouldn't matter what method you use. You will get the same answer in both cases. like I said, if you prefer one method or the other, I guess, it'd be best to learn both methods, because that way on the exam, on the written exam or something anyway, you can do it both ways, and if you get the same answer using method 1 and then method 2, right, you probably got the right answer, because there isn't really a way to check these like there are with equations, right? There's nothing you can plug back into to see if your answer is correct. But if you would prefer to just learn one method or the other, if you find it too confusing to learn both of the methods, you can certainly use one. Again, I'm probably not going to say on the exam use method 1 or method 2, right? I'm just going to give you a complex fraction like this and just say simplify it. So let's do this example, and then we might actually do some of the same examples using method 2, but let's do this one using method 1 again. So in this case, right, the fraction on the bottom is already combined into a single fraction, so I don't need to do anything with that. Now for this one, what I would need to do is, this is really 6 over 1, so just ignoring the bottom and looking at the top, I'd have to multiply the top and the bottom by x to get the common denominator of x. So just doing that, and then adding things together, right, so I'll get basically 6x over x. Adding things together, right, I'll get 6x plus 2 over x. Now I've got it written as a single fraction divided by single fraction. Flip the bottom fraction over and multiply, and then just reduce. You might notice you can factor a 2 out of each term here, leaving you with 3x plus 1, which will conveniently cancel out with this. Right? You cannot cancel the 2 and the 4 because they're both on the top. So you'll basically get 2 times 4, which is 8, over x. Sorry, I guess this typo here, right? That shouldn't be there, right? So it should just give you 8 over x, right? Because this is going to cancel with that. So let's look at another example, right? So again, with this method using example 1, or method 1, right? Again, we want to look at the top. Just ignore the bottom and look at the top fractions, right? What's the common denominator there, right? The common denominator there would be x squared y squared. So you'd multiply on the bottom by y squared, the top by y squared here. Here you multiply on the bottom by x squared and the top by x squared. If you look at the bottom two fractions, the common denominator there would be xy. So multiply by y here and x here. Okay, so if you do that, you'll get this, right? And then again, you would just add the fractions together. So it's just going to be y squared minus x squared over x squared y squared. Here you'll get y minus x over x squared y squared. Flip the bottom fraction over and then multiply. And again, here you might be able to reduce before you multiply. This can be factored. So the y minus x here will cancel with the y minus x here. And then this xy should cancel with one of the x's and one of the y's, leaving you with yx on the bottom. So you'll basically get 1 plus x times 1 over y times x. And again, you can leave it in parentheses if you want, but you don't have to. So then that should give you the answer. All right, so we've taken this complex fraction and simplified it to this fraction, right? You can see that the final answer is quite a bit less complicated than the original answer. Okay, so that was method 1, right? So method 2, again, you should get the same answer, but it works a little bit differently, right? Remember in method 1, you basically added the fractions together on the top, added the fractions together on the bottom, or subtracted as the case might be, and then you flip the bottom fraction over and multiply. For method 2, what you do is you look at all the fractions sort of within the larger fraction, look at all the denominators of those fractions, and trying to find the LCD of all the fractions within the larger fraction. Then you multiply both the top and the bottom, both the numerator and the denominator of the complex fraction by that LCD, and that should again give you the same answer. So let's look at an example here. So let's say I want you to simplify this and simplify this fraction by using method 2. Now we certainly could use method 1, but we're just going to use method 2 in this case. So what you do for method 2 is just look at all the denominators here within the big fraction. So look at the 8, 2, 8w, and 4, and try to find out what the common denominator is for those things, right? Well, 4 and 2 both go into 8, so it should be 8w if you think about it, right? Then what you do is you multiply the top here and the bottom here by 8, sorry, not 8 over w, should be 8w. Multiply the top and the bottom by 8w, and then just reduce, right? So you'll take the 8w times that, the 8w times that. Same thing here, you'll take the 8w times that and the 8w times that. So if you do that, you'll get 8w squared. So again, basically what's going to happen is this 8 and that 8 will cancel. and then you take the 8w times this. 2 goes into 8 4 times, so you'll get 4w there. On the bottom here, again, the 8 and the 8 will cancel, so will the w, so you'll basically get 3 here, right? You'll get 24w over 8w, and then you'll get 8w times 3. That gives you 24w over 4. Well, 4 goes into 24 6 times, so this will simplify into w squared minus 4w over 3 plus 6w. And again, you can factor the top and the bottom. Now, whether anything's going to reduce or not is a good question, right? I guess if you look at this particular problem, right, you can factor a w out of the top. You'll be left with w minus 4. In the bottom, you can certainly factor a 3 out. That'll leave you with 1 plus 2w, but there's nothing you can do to reduce that. So you can just leave it in this form, but again, you might want to factor it just to be sure. So I'll let you write the answer in either form. Doesn't matter. But make sure you try to reduce the fraction as much as you can. So let's go back and do this other problem that we did using method 1, just to show you that we get the same answer, right? So the answer for this one, at least if I hadn't messed this up, right, should have been 8 over x, right? Because this should have canceled with that, but I forgot to cancel it here. So, using method 1, we got 8 over x. You should get the same answer using method 2, right? So again, it shouldn't matter what the method is. So remember, for method 2, what we do is we look at all the fractions within the big fractions, right? So here the denominator is 1. Here it's x, here it's 4. So what's the smallest thing that 1x and 4 will go into? Well, the smallest thing it will go into is 4x, right? So you multiply everything on the top here by 4x, and everything on the bottom here by 4x, and and then just reduce that, right? So you'll take 4x times this, 4x times this, right? So this will give you like 24x. Here the x's will cancel, so you'll just get 8 here. And then here the 4 will cancel with the 4, so you just take the x times the 3x, which will give you 3x squared plus x. So just to work that out in the next slide here, again, you would find the LCD, which would be 4x, and then multiply everything on the bottom by 4x. So you'll multiply the top and the bottom by 4x here. Now remember, what that really means is 4x over 1, right? Because you have to take this times the top, right? You do not take this times the bottom. It's times the top of both fractions. And remember, this is really 6 over 1, right? So, just writing it that way, I guess I don't know why I had this step in here twice, I guess, but so multiplying that through, right, you'll get 4x times 6, 4x over 2x, 4x times 2 over x, and then here again, this 4 and that 4 will cancel, so you'll just basically get x times 3x and x plus 1. So essentially what you'll get is you'll get 24x here. Here the x's will cancel, so you'll basically get 4 times 2 or 8. Right here, you'll get x times this, which is 3x squared plus x. And then again, if you look at this answer, you might say, well, that doesn't look like the answer we got before, right? Because remember, the answer that we got before was 8 over x, right, I think. So just going back to that slide, right, we did get 8 over x. Well, remember, don't forget to reduce your fraction, right? So you might notice that you can factor an 8 out of the top, an x out of the bottom, and then those will cancel, and you do get the same answer, right? So, like I said, a good thing to do on the exam is, if you be better to learn both methods. That way, if I give you a problem like this on the exam, you could do it using method 1, and then do it using method 2. If you get the same answer using both methods, you probably got the right answer, right? There's no guarantee, I guess, if you make a mistake, but and I guess if one of the answers isn't the same, you have to go and figure out where your mistake is, but that's really the only way you can kind of double check this. So let's also do this other example that we did before using method 1. So again, in this case, with the method 1, we would have added these fractions together, or subtracted in this case, and then flipped over and multiplied. But remember, for method 2, we want to look at all the denominators within the big fractions. So look at x squared, y squared, x, and y. What would the LCD of those 4 things be? Well, it should be x squared times y squared, right? Because both x and y will go into x squared, y squared, and so will x squared and y squared. So you basically take your fraction and multiply on the top and the bottom by x squared, y squared over x squared, y squared, right? I'm just multiplying by 1, so I can do that, right? I mean, I'm not changing the value of the fraction as long as I multiply on the top and the bottom by the same thing, right? So here I can write this as x squared, y squared over 1, x squared, y squared over 1, and then just multiply through. All right, so you'll get x squared y squared over x squared y squared over y squared. Here I'll get x squared y squared over x squared and x squared y squared over y. And you don't have to write every step in here if you don't really want to, right? You might be able to do this in your head. Like you might notice, well, when I multiply this through, right, the x squareds are going to cancel. So if you can just jump down to this step, as long as you don't make any mistakes, that should be okay. And then, right, same thing here, the y squareds will cancel, so that will leave you with y squared minus x squared. Here this x will cancel with one of those x's, leaving you with xy squared, and this y will cancel with one of those y's, leaving you with x squared y. So again, if you look at this, this is still not the same answer that we got before, but remember, don't forget to reduce. The top is factorable into this. The bottom, you can pull out a common factor of xy. That'll leave you with y minus x. And if you do reduce the common factors, you get the same answer that we got before, which is y plus x over xy, if you look back at that previous example. So here's an example using method 2. So let's maybe look at some other examples here. And we'll maybe switch things up and use method 1 or method 2. Like I said, I prefer method 1, so a lot of these I'll do using method 1. But maybe we'll go through and do a couple of these using either method. So if you look at this one, right, there's really nothing to do for this problem. And you'll probably start out with these simple problems like this, right? You don't really have to add or subtract fractions here. So all you really have to do is just flip the bottom over and multiply, right? So flip the bottom over and multiply and then just reduce, right? 3 goes into 9 3 times, 2 goes into 4 twice. That y will cancel with that y. That x will cancel with one of those x's, leaving you with 3 times 2 over x times y on the top. Oh, I guess that y shouldn't be there, sorry. Right, because those y's are going to cancel. So that will just leave you with 6 over x there, right? And you could do method 2 on this, right? I guess if you did method 2, you'd look at the LCD for 2x squared y and 4xy, which would be 4x squared y. You could multiply on the top and the bottom by that, and that would also give you the same thing. But I think method 1 is a lot easier in this case. Here's another example. Let's use method 1. So in this case, the LCD is for the top is x squared. So if I subtract these two things, I'll get x squared minus 1 over x squared because I'm multiplying on the top and bottom by x squared here. I've got this written as a single fraction, that written as a single fraction. I would just flip the bottom over and multiply. This is factorable. Cancel those things, right? That x will cancel with one of those x's, leaving you with x plus 1 over x. And again, you could maybe do this using method 2, maybe just to do method 2 up here. I don't know if I'll do all these using method 2, but so if you look at the, I think sometimes method 2 can be a little bit faster, depending, especially if you have more complicated fractions. But in this case, the LCD in this case for all of the fractions, here the denominator is 1, so you've got x squared and x. The LCD for that would just be x squared. So I'd multiply on the top by x squared, multiply on the bottom by x squared. So if I multiply that through, right, I'll just get x squared times 1, which is x squared. Here this is going to cancel with that, so I'll just get minus 1 on top. Here this x squared is going to cancel with one of those x's, so I'll be left with x minus 1 times x, and then just factor, right? So the top will factor into x minus 1, x plus 1, and I'll get x minus 1 over x on the bottom, so I'll get x plus 1 over x. And so either way I do it using method 1 or method 2, I do get the same answer, right? Remember, you cannot reduce this because, remember, you can only reduce when you're multiplying things together, and here you're adding, right? If it was x times 1 over x, then I could reduce. Maybe just to do another couple of examples, this might be a tricky one that you might run into at some point. So I wanted to go over an example of something like this. So let's say you want to take 1 over x plus 5 minus 1 over x over 5, and you wanted to simplify that. Well, I think the hard thing here can be finding what the LCD is, right? I mean, there's really nothing to simplify in the bottom fraction. That's really 5 over 1. So the question is, well, what is the LCD for x plus 5 and x, right? You might say, well, isn't it just x plus 5? Well, be careful, right? I mean, this is, imagine that x was 2. That would be like saying the LCD of, 2 plus 5, the LCD of 7 and 5 is 7, right? But 5 doesn't go into 7. So just because this number is 5 more than this one doesn't mean this goes into this one, right? I mean, so this, this is basically taking the number and adding 5, not multiplying by 5. So it turns out that the LCD for the top in this case will be x plus 5 times x, just like the LCD here for this would be 7 times 5, not just 7. So I need to multiply on the top and the bottom here by x, and I need to multiply on the top and the bottom here by x plus 5. So if I do that, I'll get x minus x plus 5 over the common denominator of x plus 5 times 5. Here I can distribute, and the x and the negative x will cancel, so we'll just get negative 5 on top, and then flip the bottom fraction over and multiply. Right? So flip that over and multiply, that'll cancel with that, and I'll get negative 1 over x times x, or x plus 5 times x, and I can distribute that x through if I want, or you can just leave it that way too. So I would take either one of those as an answer. So the idea in this case, again, is you could use method 2 on this as well, but you might run into some problems like this, and people tend to have a little bit of trouble with these. So if you have problems like that, right, the LCD again in this place will not just be x plus 5, it's x plus 5 times x. Here's some more examples. Maybe just to do these quickly, I'm just going to use method 1. So for this one, the LCD would be x. So I'll get x squared plus 1 over x. For the bottom here, the LCD is x, so I'll get x squared plus 4 over x. Then I would just flip the bottom fraction over and multiply. So I get x over x squared plus 4. The x's will cancel there, and I'll get x squared plus 1 over x squared plus 4, right? And again, I cannot reduce that, right? I can't factor either one of those, right? Remember, if you have x squared plus 1, at least at this point it's prime. Same thing if you have a squared plus b squared on the bottom, you can't factor that either. So you can't cancel the x squared, so that would be all the further you could go. And again, you get the same answer if you use method 2. Just for something a little bit different here, let's maybe use method 2 for this one. So if you look at all the fractions within the big fraction, the only denominator you have really is x plus 1. So what I'm going to do is take my original fraction and just multiply on the top and the bottom of everything by x minus 1, right? So in this case, right, I'm using method 2, so I'll multiply the top fraction by x minus 1, bottom fraction by x minus 1. So if I do that, x minus 1 times this, we'll get rid of the x minus 1, then I'll get 2 times x minus 1. Then on the bottom, I'll get x minus 1 times this, which is 2, minus 2 times x minus 1. Right, then just go ahead and simplify, right? You can't really cancel anything here yet. So you'll get 2 plus 2x minus 2 over 2 minus 2x plus 2. Combining like terms on the top, the 2's will cancel, so you'll get 2x on top. Same thing on the bottom, or no, I guess these don't cancel, right? So you'll get minus 2x plus 4. Right? And that's basically your answer, except don't forget to reduce, right? So you can factor a 2 out of the bottom and out of the top. If I factor, say, a 2 out of the bottom, you could factor out a negative 2, I guess, if you want, but I'll get negative x plus 2. That 2 will cancel with that 2, so I'll be left with x over negative x plus 2. Right? And again, you cannot cancel the x's there. And again, you should get the same thing if you use method 1. Whatever you think is easier, whatever you prefer, or again, it's better to do it both ways if you can. Here's some other examples, especially for problems like this where you have a lot of fractions in here. It might be better to use method 2. Again, you don't have to do it, but let's maybe just do this one using method 2. You'll get the same answer if you use method 1. So in this case, if you look at the LCD here, right, it should be y squared times 15. Right, because y goes into y squared. So just copying down the original problem here, after I've done that, I just want to multiply on the top and the bottom by 15y squared. Right, so if I do that, I'll multiply on the top and bottom here by 15y squared. Same thing for this fraction on the bottom. So if I do that, right, the y squareds will cancel here. I'll get 15 times 2, which is 30. Here this y will cancel with one of those y's, and I'll get 3 times 15, which is 45. So on the top, I'll get 30 minus 45y. And then on the bottom here, the y squared will cancel with the y squared, 5 will cancel with the 15 there, so that will give me 3 times 2, right? So that'll give me 6. Same thing here, 3 goes into 15 5 times, so I'll get plus 5y. And then, again, don't forget to reduce, right? Maybe this isn't reducible. Now, if you look at the bottom, there's nothing you can factor out of the bottom because they don't have any terms in common. But if you look at the top, right, you could factor out, looks like maybe a 5 out of each term on the top, right? Maybe you can factor out something bigger there. But that would leave you with 6 minus 9y, right? So again, doesn't look like there's anything you could cancel there. Oh, I guess you could pull out another 3, so that'll give you 15, right? So you get 3 minus, or sorry, 2 minus 3y, right? You still can't reduce anything though, so again, that would be your final answer. Again, if you want to write it in factor form, right, you could write it like that. And again, you know, you could get the same answer using method 1. Let's look at another example here. So for this one, you've got negative 6 over x squared plus 5x plus 6. That's already a single fraction. Let's just use method 1 in this one. So here the common denominator is x plus 3 times x plus 2. So I need to multiply in the top here by x plus 2 and negative 3 times x plus 3. That'll be all over my common denominator of x plus 3 times x plus 2. Right, then just go ahead and write this as negative 6 over x squared plus 5x plus 6 over, flipping this fraction upside down, right, I'll get x plus 3, x plus 2, and then simplifying this, right, I'll get 2x minus 3x, which is minus x, and then I'll get 4 minus 9, which will give me, what, minus 5, I think. You might want to double check my arithmetic on this one, but you'll get negative 6. Factor in the bottom here, that'll factor into x plus 2, x plus 3. So you'll notice that this will cancel with everything on the top here. And I could factor a negative out of each term on the bottom. I don't know if I need to do that, just to make each one of those positive, but that'll cancel with that. Or sorry, this will cancel with that, that'll cancel with that. So I'll be left with negative 6 over negative x minus 5. And again, you could pull a negative out of the top and the bottom. I don't know if this is really simplifying it, but you could write it with positive things there and write it as 6 over x plus 5, right? So, you know, imagine, you know, and so the main reason why we're doing this, imagine that you had this fraction and you had to add it to another fraction, right? I certainly wouldn't want to do it this way, but you could maybe simplify the fraction. Like, let's say you need to add this to, say, 1 over x plus 5, right? It'd be a lot easier to reduce this and add it that way, right? Because then they'd have the same common denominator. Maybe just to look at a couple more complicated examples here. Here's an example, and this tends to throw people, but if you think about what this really means, right, remember that something raised to the negative power, like a negative x, is the same thing as 1 over x. So you can write this as 2 over x plus 2 over y, and then x over y minus y over x, right? And then use method 1 or method 2. We'll look at the solution to that on the next slide. Now, there are a couple problems at the end that involve applications. Like, it turns out that if you had electronic circuits in series, if you have like an electronic circuit here where you've got some resistors in here, so a resistor is something that resists the flow of electricity, and that's usually measured in ohms, after the German scientist Ohm. But let's say that this resistor has a resistance of R1, this resistor has a resistance of R2, and this has a resistance of R3. You might assume that the resistance for the entire circuit is just that plus that plus that, but it turns out that that's not how it works. It turns out that the answer will be 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. So all these subscripts here just indicate is these three things could be 3 different resistances. So simplifying this is kind of like simplifying the equation 1 over 1x plus 1 over 1y plus 1 over or plus 1 over z, right? Because you don't know if these resistances are all the same or if they're all different. So if you wanted to find the resistance in the entire circuit, you would have to simplify this expression. So just like here, the common denominator would be x times y times z. Here the common denominator would be R1 times R2 times R3. So just to solve these, let's look at the next page here. So again, for this first one, like I said, you can rewrite it like this, which makes it a lot easier, right? Then using method 1, I'd have to multiply on the top and the bottom by y here, top and the bottom by x here. Here I'd have to multiply on the top and the bottom by x, and the top and the bottom by y here, right? So that would give me 2y plus 2x over the common denominator of yx. Here I'll get x squared minus y squared over yx. Flip this bottom fraction over, factor, you can pull a 2 out here. Here this is a difference of squares, right? Those two things are going to cancel with each other, and that'll cancel with that, leaving you with 2 over y minus x. Like I said, for this one, right, the LCD in this case would be R1, R2, and R3. And you could certainly, might even be easier to do this using method 2, but I chose to use method 1. So the LCD in this case would be r sub 1 times r sub 2 times r sub 3. So you'd have to multiply on the bottom here by r sub 2, r sub 3. And again, whatever you do to the bottom of the fraction, you have to do the top. So I'd have to multiply the top there by r sub 2, r sub 3. Here I'd multiply by r1, r3. Same thing on the bottom. Here I'd multiply by r1, r2. Same thing on the top. Right? So if I do that, I'll just get R2, R3 plus R1 plus R3 plus R1 plus oh, sorry, this should be an R2 here, sorry, plus R2, and then that's going to be all over the common denominator, right? Then I'll just flip this fraction over and multiply, right? You can really think of this as 1 over 1. So, but if I flip it over, I'm basically just multiplying by 1, and that gives me the final answer, which would be the resistance in the entire circuit. And again, this should be R sub 2 here. These should, all the subscripts should be different here. So you might run into some problems like that where they give you an application. You know, in case you're wondering where you would ever use this stuff, I don't know if anybody's going into electronics, but you can see where it would definitely be useful. So if you guys have any questions or anything about that, just let me know. All right, so that wraps up the section. So like I said, don't forget there's 2 different methods here. Again, I don't care which method you use, if you want to just learn method 1 and not learn method 2, or if you want to learn method 2 and not learn method 1, that's fine. You know, if you find it confusing to use 2 different methods, which is fine, so if you just want to learn one method, that's great. But if you might want to learn both methods so you could check your answer in case you want to. Okay, hope that makes sense. Like I said, if you guys have questions or anything, don't be afraid to contact me. All right, good luck.